Bismillahirrahmanirrahim. Dear students, so let's start from zero order kinetics. So zero order kinetic means that a constant amount of drug is eliminated for unit times. In this case, the supply of enzymes, so they are limited in the body. So with increasing the dose, a time will come when the supply of enzyme gets saturated. So at this point, no elimination reaction will take place. The biotransformation or excretion, so they remain constant at this point, especially in case of zero order kinetics. So there is a little bit difference between zero order kinetics and first order kinetics. As we have already talked about the first order kinetic, that the rate of reaction, this is directly proportional to the concentrations of the drug. So let's suppose it means that whenever the concentration of the drug they are going to increase, so the rate of reactions will be increases. While in this case, the concentrations, the constant amount of drug is eliminated per unit times due to certain reasons. And zero order kinetics, so the rate of process or reaction that is not proportional to the concentration, it means this is independent. This is not dependent on that rate of reactions. This process showing such kinetics which are known as rate limited or zero order, or you can say saturated kinetics. So it means we cannot saturate it further, so a time will come that no elimination will be occurs. Sometime clinically it is called non-linear kinetics. It means that zero order kinetics also called non-linear kinetics. And zero order kinetics, all enzymes mediated process show this type of kinetics. Phase diffusion like process do not show this type of kinetic. For example, aspirins, acetylsalicylic acid, ethanol and phenytoin, etc. So it means that the phase diffusion like process do not show this kind of kinetic, and these are the drugs. Look at zero order. This is the graphical representation. So in this graph I have mentioned that the constant amount of the drug will be eliminated here. So look at here on x-axis, you can see this is what? This is the time per hours, time in hours. While on y-axis you can see these are indications 10, 20, 30. So now let's suppose in this case we will remove we will remove 12 hours to decrease the plasma concentration by 15 microgram per ml. It means look at here, in this case the total concentration or the total amount of the drug, that is 80 microgram per ml. So it means that in this case after 12 hours to decrease the plasma concentrations 15 microgram per ml. So let's see here, this is the total. Let's suppose this is the total concentration of the drug, which is 80 microgram per ml. Now with the passage of time, so after first 12 hour, or you can say after first half-lives, the concentration of the drug was reduced to 65 microgram per ml, and the drug which is going to reduce, that is almost 15 microgram per ml. After that, after second half-life, the concentration of the drug was reduced to 50 micrograms, and then after that in third half-life it becomes 35. Mean that after each 12 hours the concentration of drug was reduced. And look at here, this these lines, this shows straight lines. So it means that the constant zero order kinetics show that a constant amount of drug will be eliminated from the body. This is another classical example. So look at here in zero order kinetics. So this is the time period, you can say time in hours, and these are you can say the concentrations of the plasma, you can say the total concentration. So look at here 0, 10, 20. So it means that after first half lives the concentration of drug was reduced. So the total concentration of the drug was how much? That was almost 80. So from this the concentration concentration was reduced up to 40% and first half lives, and then in second half life the concentration was reduced up to 30%, and then after second half life the concentration of the drug was reduced up to 20%, and you can say after third half life the concentration of drug was reduced up to this is clear 20%, and after four, you can say after four half life the concentration was reduced up to 10%, and this is the fun, and this is the straight line zero order kinetics, and with the rate of reaction is independent on the concentration of drug, and the rate of elimination of drug will be occur at the constant rate. Now come to our drug clearance. As we have we remember that half life is equal to 0.693 multiplied by volume of distribution divided by drug clearance. So now drug clearance can be defined as, for most drugs the clearance is constant over the concentration range, but the elimination is not saturable. The rate of drug elimination is directly proportional to the concentration. So now it means that the rate of the elimination is directly proportional to the concentration. So it means the greater will be the concentration of the drug, so the rate of reaction will be fast, and it means that the drug will be quickly eliminated. And in this case, so this is usually referred to the first order eliminations. Look at, see here, area under curve, clearance. In other words, when the clearance, let's suppose if the drug clearance is first order, so what does it mean? It means that the rate of drug elimination is directly proportional to the concentrations. So in this case, when clearance is first order, when the reaction is first order, so it can be estimated by calculating the area under curve of the time concentration profile after a dose. So how? It means that the clearance is calculated from the dose divided by the area under curve, which I have already mentioned in my previous study, that and how much period of time the drug will covers how much area. So it's called area under curve. So clearance is simply calculated from the dose divided by the AUC. Clearance, in other words, it can be defined that the ability of the organs of elimination. For example, as we know that kidney as the organ which is responsible for the elimination of drugs. So and the second one is liver. So liver to clear the drug from the bloodstream. So simply we can say that the ability of organs of eliminations, for example kidney, liver, to clear the drug from the bloodstream. Volume of the fluid which is completely cleared of a drug per unit time. So this is called clearance. It can be represented mathematically. These units are liter per hour, or you can say liter per hour per kg according to the condition. So pharmacokinetic term used in the determination of the maintenance dose. Clearance is not the measure of re-equilibrium of the body within various body compartments, but rather than the actual removal of the drug from the body with time, usually by hepatic metabolism or by renal excretion. So there are different pathways through which the drug can clears in a particular period of time. Clearance can be also defined as that the volume of the blood in a defined region of the body that is cleared of a drug in a unit times. While clearance is a more useful concept in reality that T-half, or you can say elimination constant, since it takes its accounts blood flow rate, clearance variety with the body weight, and also varies with degree of protein binding. So already you have remembered bloods, that we can easily say that clearance can also deviate, it can also alters with the body weight. So depend upon on your body weight, that how much drug that is cleared for unit time. So that also depend upon on the volume of the bloods, or you can say the weight of the individual. So it carry also varies with the degree of protein binding. Look at, so at the end of lecture, so I would like to say that at the end of the lecture my students will be able to understood these things, to discuss the clinical significance of half-life with examples, to discuss the clinical significance of steady state concentrations with example, and to discuss the clinical significance of the clearance and kinetics of drug elimination with example. So thank you so much for watching this slide.